So, as I was saying, the types of things that an access list can filter on. Many, many different things. It just depends on what type of access list you're creating. All right? So it says here packet filtering is called static packet filtering. There is an option to do something called dynamic packet filtering, but we need a firewall to do that. A dynamic packet filter is a packet filter that can adjust to dynamic situations of packet flow. A static packet filter never changes. It's always filtering on the exact same characteristics. The downside to using a static packet filter is they're easy to bypass if you can somehow spoof an IP address or a MAC address or whatever it might be. All right? So routers act as packet filters when you apply an access list to a router interface. Those routers will act as packet filters. All right? Now, an ACL stands for Access Control List, is a sequential list of rules or statements. Those statements are called access control entries. And each access control entry represents an action that we're going to take against a packet based on packet criteria. What are the two actions that we have to choose from? What are the two actions that a packet filter has to choose from? Allow and deny, right? Permit or deny. And it doesn't matter what kind of access list it is. It could be an extended access list, a standard access list. It could be IPv6, IPv4, MAC, doesn't matter. All access lists do one of two things. They either permit traffic or they deny traffic. All right? Even a classification ACL permits or denies traffic. What is a classification ACL permitting or denying? If it's not actually filtering traffic, like a security policy, what does a classification ACL permit or deny? It permits or denies traffic to be classified. So for example, this traffic I'm going to NAT, this traffic I'm not going to NAT. Use an ACL to define that. A permit in the classification ACL means NAT this traffic. A deny in the classification ACL means do not NAT this traffic. You guys see what I'm saying? Good? One of the golden rules, traffic generated by the router itself can never be filtered by an ACL on that router. That would cause all kinds of problems because you'd have EIGRP traffic being filtered, you'd have OSPF traffic being filtered, CDP, all kinds of stuff. So Cisco has made that kind of a standing rule. We never filter traffic that's originating on the router itself. When it comes to traffic classification, it's really no different. The only difference is instead of actually applying a rule to traffic that allows us to block or permit traffic, we're applying rules to traffic that allow us to apply a policy to that traffic. For example, in the CCNP class, if you guys ever get down to that level, you're going to learn about policy-based routing, where you can actually create an access list, tie it to a route map, and then you can actually tell the traffic, okay, this traffic needs to go to this gateway, this traffic needs to go to this gateway. That's another example of how we might use a classification ACL. All of the rules that apply to a classification ACL apply to a filtering ACL. A permit means to classify, a deny means to not classify. All right? So that's what it says here. A permit generally means that the traffic will have a policy applied. A deny means that the traffic will not have a policy applied. Now, there are 4 types of access lists that you guys are going to have to be familiar with the exam. This is the raw syntax. And looking at raw syntax to figure out how to write an ACL is not good. It makes it extremely difficult to understand access control lists. So I'm not going to spend a whole lot of time on this slide. What I want to point out here, though, that their access lists have generally two processes that you have to complete in order for an access list to be effective. Number one, you have to create the access list. We have named and numbered access lists. We'll look at that later. But creating an access list doesn't do anything. In order for the access list to actually do something, you have to apply it. Okay? You have to apply it to an interface. You have to apply it to a process. So creating an access list by itself doesn't do anything. We're, of course, going to look at lots of examples as we go through the chapter. So this particular slide is more for your information later on. It may not make perfect sense right now. It may not make any sense right now. But we're going to investigate the details of this as we go through the chapter. If you're using an access list for filtering, there are two configuration steps that have to take place. You need to create the access list globally, and then you need to apply the access list to an interface. You can apply an access list in either the inbound direction, so it's from the perspective of the router coming into the router, or you can apply an access list in the outbound direction. But there is a rule here. It's called the 3 Ps rule. You're only allowed to apply one access list per interface, per protocol, per direction. The 3 Ps. Now, what does that mean? One access list per interface, per protocol, per direction. So if this is a fast Ethernet 00 interface, I can apply one access list inbound, if it's IP, or I can apply an access list outbound, but I can't apply 2 access lists inbound, or 3 access lists inbound, or whatever. Can you have an access list or 2 access lists on an interface? Absolutely. You can, if one access list is inbound and one access list is outbound. Does an access list that's applied in the inbound direction have any effect on traffic flowing in the outbound direction? Does an access list applied in the inbound direction have any effect on traffic in the outbound direction? No. Okay? So those are distinctly different applications of the access list. All right? Per protocol means protocol stacks, IPv4, IPv6, etc. There are several types of access lists. We're going to take a look at the legacy type first, which are what we call numbered ACLs. Numbered ACLs are traditionally how we created access lists. You would go into global configuration mode, and you would start to write your access rules. The number 10 that you see there is the access list number. It's not a line number. So by using 10 multiple times, essentially what we're saying is we're creating a 3-line access list. How does the router know how to process that access list? If an access list has multiple lines, how is it processed through the router?
From the top down until it matches.
Yep. Access lists are always, always, always processed from the top down. When there's a match to a rule, we stop processing the access list for that packet. We don't search the entire access list to find a better rule. So the order of your entries are very important. For example, you don't want to permit the 1010 subnet first and then deny the 1010 host second, right? You don't want to permit the 1010 network first and then deny the 1010 host. And actually, in most modern iOS, it won't even let you do that anymore. Okay? Let me show you guys what I'm talking about. Hopefully, Packet Tracer won't make a liar out of me. Okay? Config T, access dash list 10, permit 10, 10, 0, 0, 0, 0, 255, 255. We'll talk about the syntax a little bit later on. But you guys kind of have an idea already how wildcards work, right? We talked about wildcards with network statements. It is a lot different in an access list, though. And then I wouldn't do this, right? Access list 10, deny host 10, 10, 10, 10. Of course, Packet Tracer made a liar out of me. It took that, most modern iOS, if I open up GNS3, I'm not going to because I don't want to waste a whole lot of time, but if I were to open up GNS3 and go into a 15-code router, it would actually say, you can't do that. The router's smart enough to know you just allowed the entire 1010 subnet. There's no way you can deny the 10.10.10.10 host after that because that host was allowed by the first rule. See what I'm saying? So the general rule of thumb is that your more specific statements go towards the top of the access list. I said I wasn't going to open up GNS3, and I actually am because I want to use a real router to demonstrate these concepts throughout the rest of the chapter. I'm a little bit tired of Packet Tracer making a liar out of me. So I'm going to use real iOS. I mean, it's simple, right? Just a router. Being able to create access lists effectively is kind of an art form. But all the things that we've been talking about over the last 5 days kind of culminate into the ability to create these access lists effectively. Okay? Understanding block sizes is useful. Understanding binary math is useful. Understanding the concepts of a wildcard mask is useful. Understanding how packets are formatted and headers are formatted. It's all useful. All right? Access dash list 10, permit 10, 10, 0, 0, 255, 255. Oh, sorry. I'm doing it like on an ASA. All right? Access dash deny host 10, 10, 10, 10. All right? And that's the error that I was referring to. All right? An access rule can't be configured at a higher sequence number as it is part of the existing rule at sequence number 10. In other words, what they said is, you're stupid, right? You can't create a second rule that's part of the first rule. All right? So there are two types of access lists that exist in the traditional method. Standard ACLs, they're going to range from 100 or 1 to 99, and extended ACLs are going to range from 100 to 199. It's very important that you guys know what these access lists have the ability to filter on. A standard ACL can only filter on one thing. I'll move this microphone back over. Standard ACL can only filter on one thing. Source IP. Source IP. The easy way to remember that? Standard starts with an S. Source IP starts with an S. Maybe that's a good way to remember it. I don't know. All right? So there's a very limited use for standard ACLs. Usually a standard ACL is going to be used for traffic classification. It's not going to be used for advanced packet filtering. An extended ACL has the ability to filter on protocol, source IP, destination IP, source port, destination port, all kinds of things. That's the one that's a little bit more challenging because you have to remember the order of the rules or the order of the statements. And that can be a little bit challenging sometimes. The way that we typically create access lists today is we use these things called named ACLs. Let me demonstrate. And named ACLs tend to make more sense. Logically speaking, a named ACL is no different than a numbered ACL. The way that they filter traffic, the way we classify traffic, it's no different. It's just the way that you enter the statements is slightly different. So I might go, instead of access list 10, right? I might go IP access dash list standard because I'm creating a standard ACL, and I'll give it a name. And the nice thing about being able to give it a name is that when you reference that name later on, you understand kind of where you're coming from with regard to the ACL. Now at this point, we don't use access list numbers because notice I'm in a sub-configuration mode. I'm now configuring this access list kind of in a sub-configuration mode. So I can still do the permits or the denies. I'm going to do it correctly this time. I'm going to say deny host 10.10.10.10, and I'm going to say permit 10.10.0.0.0.255.255. Notice that that was allowed because I followed the rules. I put my more specific rule at the top. I can also create an extended named ACL by saying IP access list extended ACL 1 extended block bad juju. All right? Now the syntax for an extended ACL is much more complex because it's not just source IP. I can say permit TCP, that's a protocol, from host 10.10.10.10 with a source port of 4500 with a destination of 192.168.10.0, 0.0.0.255, and a destination port of 80. I forgot my EQ. So you can see that you have a lot more granularity when it comes to, let me do a show access list real quick so you can see that whole line. You can do a lot more with an extended ACL. I'm permitting a specific protocol from a specific host using a specific source port. That's very, very rare, by the way. Why do we usually not filter on a source port?
They're usually ephemeral.
They're always ephemeral. They're random, right? But you're correct. They're random. So it's very difficult to filter on a source port, unless a specific application is programmed to always use a specific port. Destination network, destination port. What does the EQ stand for? Equals. You can do less than, you can do greater than, you can do a range, or you can do equals. So far, so good? It's a lot of information, trust me. Access lists are like math. You just have to practice them. You have to get used to creating these access lists. I'm going to show you some pretty cool stuff that you can do with an access list here in a little bit. Okay? In IPv6, you can create access lists, but you cannot do it in a standard mode. In other words, the only way to create an extended access list Don Smith. That's a new name. The only way to create an extended access list, the only way to create an IPv6 access list is using an extended method. All right? Also, we don't use wildcard masks in IPv6 access lists. We use prefix lists, right? So what's happening in this particular access list? Welcome, Don. Nice of you to join us. You missed all the good stuff, but good to have you. So what is ACL3 here? I'm going to go ahead and mute you though, Don, until you have something to say, because I want feedback. What is ACL3? ACL3 is a name, right? Notice we didn't specify standard or extended. I'm going to permit TCP traffic from this subnet to anybody as long as the destination port is 80. So that is allowing web traffic from this subnet to anybody if it's port 80. Make sense? I'm going to permit TCP traffic from anybody to this host. /128 is a host-specific mask if it's equal to FTP. So anybody can FTP to that host. And I'm going to permit UDP traffic from this subnet to anybody. All UDP traffic. If I don't specify a port number, we assume that it's all UDP traffic. Question. If this access list is permit, what's the point? Is it blocking anything?
Since you specified a port on the end there, it's still going to block anything that's not that port number, right?
Why is that though? That is the question. Why is that?
Is there an implicit deny at the end of the ACL?
Exactly. At the end of every single access list, there's an implicit deny. I guess Don was not interested. Tell you what, man, all those people on that in that group, they just missed out. Sometimes they just don't know what's good for them. Right, Bernard? All right. There's an implicit deny at the end of every access list. You can't get rid of it. You can bypass it by just permitting everything explicitly, but you cannot get rid of that implicit deny. So what does that tell you about an access list with regard to having a permit statement? What if an access list doesn't have any permit statements? What if all the entries in the access list are denied? Then everything gets denied, right? So every access list must have at least one permit statement. Every access list must have at least one permit statement. Otherwise, it's just a door, a locked door, and it will drop all of our traffic. Now, you guys are not going to be tested on IPv6 access lists. You do need to know that there is no way to create a standard IPv6 access list. That's going to be on the test. I believe that's on the security test, though, not the CCNA. So let's talk about wildcard masks. The bottom line with a wildcard mask, a 1 means I care about that, I don't care about that bit. A 0 means I care about that bit. Now I've gone through and I've given a bunch of examples on wildcards and talked about the math of a wildcard and all these different slides here. But I'm going to bypass those because I want to show you the wildcard process step by step in kind of a real-time process here. Okay? forget the syntax right now. We don't care about the actual access list syntax. The way that I teach wildcards is I give you a bunch of examples and I beat it into your head until you figure it out, pretty much. Okay? So if I said permit 10.10.00.000.255, what does that match? Now this is a pretty simple one, isn't it? Zeros mean I care, ones mean I don't care. So this is going to match 10.10.10 dot 0 through 255. Does that make sense? It's like a network mask, but it's the inverse. It's like doing network statements in OSPF and EIGRP. Oops, I screwed up though. Sorry. That's what it's going to match. The first 3 octets I care about, which means whatever is in the first 3 octets of the address are fixed. Those bits cannot change. The last octet I don't care about. Those bits can be anything. Does that make sense? But the interesting thing about an access list is every octet is treated independently. You could do this, 10, 0, 10, 0, 0.255.0.255. That is perfectly legal. That's going to match 10.0 through 255, dot 10.0 through 255. You guys understand? When it comes to analyzing a wildcard mask for an access list, just look at each octet independently. I need to make sure that you guys understand this part. Yes? No? All right. Permit 10.10.0.0 0.0.3.255. Does anybody have any idea what that's going to match? Well, the way that you should do this is, and this will help you on the test as well, limit the possibilities. Write down what you know, and then try to figure out what you don't know. You guys should know it's going to be 10.10, excuse me, dot something, dot 0 through 255, right? You guys know that much, right? I guess the question is then, what does the dot 3 represent? Well, check it out. I'll show you the binary way first, and then I'll talk about the block size. What is the value of the third octet in the IP address? What is the value of the third octet in binary of the IP address?
0.0.0.0.0.0.0.
Yes, thank you. Do you guys agree with that? What is the binary value of the third octet in the IP address? What is the binary value of the third octet in the mask? Come on, you guys can do this.
0.0.0.0.0.0.11.
Do you guys agree with that? That is equal to 3. The 1 and the 2 are on. Don't overthink it, guys. It's not that difficult. It's basic binary conversions. Now, what does a 1 in the wildcard mask mean? For an access list, what does the 1 in a wildcard mask mean? It means that the corresponding bits in the address are wild. It means they can be anything. You follow what I'm saying? So, what are we matching in this third octet? Anything from what to what?
0 to 3.
Anything from 0 to 3. That's exactly right. That is literally how a wildcard mask works. And it doesn't matter what combination of ones and zeros you have. That is how a wildcard mask works. All right, let's do some more. Permit 10.0.10.0 1.0.63. I can't do that. Well, the only thing I can do is 1.63. All right, pick what you know. Let's write down what you guys know. Match something dot 0, right? Because that's an exact match. Dot something dot something. Okay? What is the binary value of the first octet of the address? What is the binary value of the first octet of the address? What is 10 in binary?
0.
Yes? It's the 8 and the 2. What is the binary value of the first octet of the mask? What is the decimal value of the first octet of the mask?
1.
1. What is the binary equivalent?
0, 0, 0, 0, 0, 1.
I think everybody was up studying late last night. Nobody's awake this morning. What does this mean with regard to what matches? It means that whatever corresponds to a 1 can be anything. You see what I'm saying? It's always that way. Whatever corresponds to the 1 in the mask can be anything, which means that the first octet is going to match what? Can't be 0 because these bits are fixed. 10 through 11. That's exactly right. 10 and 11. Remember, anything that corresponds to a 0 can't change. Anything that corresponds to an X can change. Only one bit can change here, the last bit. Which means that this one's the same, isn't it? What about the last one? What is the binary equivalent of the last octet of the IP address? What is the binary equivalent of the last octet of the IP address?
0, 0, 1, 1, 1.
Of the IP address, not the mask.
Zeros. All zeros.
What is the binary equivalent of the mask? 63
0, 0, 0.
00 1 1 1 1 1 1. If the 64 column is off, 63 means that all the bits to the right of that are on. So that means that all of these bits are wild. And what is that going to match?
0 to 63.
0 to 63. The key thing about interpreting a wildcard mask in an access list is to look at each octet separately. You always look at each octet separately. That's the way you're going to be able to break this down. Now on the test, you're not going to have to do anything like this. On the test, you're going to get wildcard masks that are contiguous. In other words, they're just going to look like a 0.0.0.255. Those are easy, all right? All right, let's do just a couple more and then we'll move on because I know you guys want to study. I'm going to give you a little bit more study time this morning before your test. I want to finish this chapter. I don't think I'm going to do the NAT chapter. I don't think that's really that important. So I do want to give you guys a chance to kind of review your questions before the test. Permit. Let's see. 192, 168. Let's do in this case 64.0 with a wildcard of 0.0.63. Giovanni, I don't believe we're going to do the NAT discussion. I think we're going to bypass that because these guys have their test at lunch and they need to study. We are going to continue with the lesson after the exam, but it'll be the security stuff. Let's do 127. Okay. You guys can participate in the security stuff if you want. That's up to you guys. If you're interested in kind of seeing some stuff about that. Let's see. What is the first octet going to match? It's an exact match, right? Second octet, also an exact match. Third octet. What is the binary value of 64? 0, 1, 0, 0, 0, 0, 0, 0. What is the binary value of 63? 0, 0, 1, 1, 1, 1, 1, 1. Got it? Which means that these are my wildcard bits. They can be anything, which means that the third octet matches what? 64 to 127. What about the last octet? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Which means these bits can be anything. Which means the last octet matches what? 0 to 127. Starting to make more sense? That's the mathematical way of doing it. You can also think in block sizes, but I don't think I'm going to confuse you with that right now. The thing about an access list is you just have to look at each octet separately. I keep saying that, but it makes your life much, much simpler. Now we're going to do one more, and I'm only doing this to give you an idea of how flexible these access lists really are. 172.144.64.128 with a wildcard of 0.240. Now let me do 205. Let's just make it even really crazy. 205.31.15. Okay? Wow. That's perfectly legal. All right. Of course, what is that going to match? 172. Let's skip that second octet for right now. What is 64 in binary? 0, 1, 0, 0, 0, 0, 0, 0. What is 31 in binary? 0, 0, 0, 1, 1, 1, 1, 1. Yes? Which means these bits are wild, x, 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 x. So that third octet is going to match what?
64 to...
Wow. Yeah. 64 to 95. Right? Because the 32nd one is 96. 64 plus 32 is 96. 32 bit is fixed at 0. So it'll only go up to 95. What about the last octet? 128 is 1, 0, 0, 0, 0, 0, 0. 15 is 0, 0, 0, 0, 1, 1, 1, 1. which means these bits are fixed, XXXX, which means this goes to 128 to what? 143? Whatever 128 plus 15 is, right? Yeah, 143. Make sense? It's pretty simple when you break it down that way, right? Just do the bit comparison. But now we get to the second octet. Now we have to do some serious comparison. 144 is 1, right? So if I take 144 minus 128, that's 16. So that would be 0, 0, 1, 0, 0, 0, 0. That equals 144, right? 205, 1, 1, yes, that's 192. 205 minus 192 is 13 more. So 0, 0, 1, 1, 0, 1. That equals 205. The rules still apply. Anything that corresponds with a 1 is a wild card. So those two bits are wild, and these two bits are wild, and that bit is wild. So what is that going to match? It's going to match all kinds of crazy stuff. It's going to match 16. It's going to match 17. It's going to match 20. It's going to match 21. What's 16 and 12? 28? It's going to match 28. It's going to match 29. How am I getting those numbers? Because this bit is on, that's fixed. 16 plus 1, 16 plus 4, 16 plus 5, 16 plus 8, 16 plus 9, 16 plus 12, 16 plus 13. You get what I'm saying? It's still the exact same rules. The wildcard bits can be anything. All right? This is called bitwise masking. Bitwise masking. It allows us to kind of specify, and by the way, 144 in the rule is going to get converted to 16. So if I write my permit rule, the router is actually going to change that to 16. Let me prove it to you. Exit. Access-list 10. Well, let's do 20. Permit, and I'm just going to copy this and paste it. It takes it, do show access-list 20. It converted it to a 16. Why did it convert it to a 16? Because the 144 bit, or the bit that made it 144, corresponds to a wild card. So the router just puts it at the least common denominator, which is 0. See what I'm saying? The router is smart enough to say, well, it doesn't matter if that first bit is on or off, so we're just going to assume it's off. That's our starting point. So even though you put 144, the router changes that to 16 because that's the only bit that's fixed. Make sense? Certainly well above and beyond what you're going to need to know for the exam, though. If you ever go take your CCIE, you'll have to know stuff like this. When I did my CCIE routing and switching lab, they had me redistribute routes from one protocol to another, but they said you can only redistribute the 5th subnet, the 8th subnet, the 12th subnet. They picked a bunch of random subnets, seemingly random subnets, and then you had to figure out the bitwise mask to actually do that redistribution because they said you can only do it using a one-line access list. So They're very specific codes. ACLs are processed from the top down. We talked about that. As soon as there's a packet that matches an entry, we perform that action. We stop processing the access list. That means that we're going to put our more specific rules at the top of the ACL and our least specific rules at the bottom. And in the newer code, you saw that that's actually not even an option. The code, the iOS is smart enough to say, hey, this rule is already being taken care of by another rule in the access list. Okay? Why does every access list have to have at least one permit? Because there's an implicit deny everything at the end. Okay? Where do you place your access lists? Extended ACLs get placed as close to the source as possible. Standard ACLs as close to the destination. Any idea why that might be true? What do standard ACLs filter on?
Source.
Source IP. So if you have a scenario where your goal in this case is to block traffic from the 10 subnet to the 30 subnet. All right, here's the 10 subnet, here's the 30 subnet. And your goal is to block traffic from the 10 subnet to the 30 subnet. If you create a standard ACL, what do you filter on? You filter on the 10, right? Because that's the source. If you were to put that access list here, inbound, what would happen to all that 10 traffic? It gets blocked completely, doesn't it? All that 10 traffic gets blocked completely because you're filtering on source. But you could put that access list here, outbound, but what's the downside to putting a standard ACL here, outbound? Is the 10 traffic still going to be able to go from here to here? Sure. Is the 10 traffic still going to be able to go from here to here? Sure. But what's happening with that traffic that goes from here to here? It gets dropped, right? We're wasting resources. We're wasting bandwidth. We're wasting processor power. Why not just create an extended access list to match on the source and the destination and drop it before it hits your network? See what I'm saying? Yes, no? All right. Okay, so extended ACLs are almost always used for filtering traffic because they're much more efficient. If they're written correctly, they're much more efficient. So, let's take a look at some examples and then we'll wrap up this chapter. In this example, I want to filter traffic. Let's see what they're doing here. First of all, it's access list 1, which means it is a standard ACL, right? And I'm denying traffic from this host. That's the source IP, right? So any traffic that has that source IP is denied. Everything else is permitted. That's the permit any. Any is a way to say essentially everybody else. Does that make sense? Where did they apply that access list? They used the ID access group to apply the access list, but where did they apply the access list? They applied it on gig 00 in the inbound direction. So the access list is applied here. The 10 traffic is allowed except for 1010. So we're not allowing the 1010 host to leave the subnet. Make sense? All right. You can also comment ACLs, but the IP can be changed. Yes, Giovanni. It's not a very good way of doing filtering because that host can change their IP and then they can get out. But it is nonetheless an example. Okay. Remarks are good. Remarks are good. You can add remarks into your access list, and we tend to try to do this because access lists can actually be very, very long. They could be literally hundreds of lines long. So by adding statements or remarks, you can kind of identify some of the actions that are taking place on the access list. Remarks are not, they don't actually do anything, but if you're reading the access list in your command line, if you have those remarks, it can be useful. Okay? All right. Now, how do I edit an access list? Back in the day, this is not the way it used to work. So let's do IP access-list extended. Edit example. Permit host 10, 10, 10, 10. Oops. I need a protocol. Oh, and I need a destination. I forgot I used to extend it, sorry. Deny TCP any EQ80. Permit UDP any EQ69. And deny or permit EIGRP any. Okay? I'm just throwing some random rules in here. Do show access dash list. Now you'll notice this edit example, when the iOS creates the access list, it adds these line numbers. So that gives you the ability to actually edit that access list in line. In the past, if you wanted to edit an access list, you'd have to delete the whole access list, edit in Notepad, and paste it back in. But now I can insert lines. I can say line 15, permit TCP any EQ 443. So if I do a show access list, I can see now I've added line 15. I can actually take out a line, no 30. Do show access dash list, and I can see that line 30 has been removed. So you can actually insert lines, delete lines. It's pretty cool. All right. You're not tested on that, but still something cool to see. How do we view an access list? Show access list. We've been using that command. You can also do a show IP interface. If you run a show IP interface, you can see if an access list is actually applied to the interface. This particular interface has two access lists applied. It has one in the outbound direction, which is a named access list, and it has one in the inbound direction, which is a numbered access list. All right. Sometimes you can see if there are matches against an access list, because when you do a show access list, you'll see the hit count, allowing you to identify that matches have been made against that particular access list. All right. And we can secure access to our VTY lines. Now, it's different, right? You create the access list the normal way, but this is on the test. When you want to apply an access list to your VTY lines, you use access class, not access group. So let's say I wanted to secure who could access my VTY lines. I write access list 10 that says permit this IP, deny this IP. And then I apply that access list to my VTY lines. So I can control who can actually telnet or SSH into my platform based on their IP address or whatever we're matching on the access list. All right. So What is this access? First of all, what kind of access list is this? Anybody? Huh? What kind of access list is it? It's extended, right? 106 is extended. I'm going to permit IP traffic from this host to anybody. And then I'm going to deny ICMP traffic from this subnet to anybody if it's a ping. And then I'm going to permit everything else. The thing about an access list that you have to understand is you have to understand how that access list is applied. Again, like I said, creating an access list by itself doesn't do anything. You actually have to apply that access list to an interface. In this case, it's FA00 inbound. So here's where the filter is applied, and it relates to the traffic coming from these clients. So all ICMP traffic from this subnet's blocked. This host is allowed to do everything, including ICMP. And then everybody else is allowed to do everything else. Make sense? All right. Heck, man. It's totally random. Goes all the way back to slide 4.